Okay, welcome back. So this is a simple announcement. Assignment 3 has been uploaded. It was uploaded last week, and the deadline is next Monday. Okay, the usual time of 11 a.m. Okay, if you have any difficulty, please always let me know. We try to be very strict about the deadline, but if you have very good reason, we will try to accommodate you. I think this is a reasonable request. Okay. So do you have any problem with Blackboard? Is everything okay? Did you see my video, by the way? Anybody? Yeah. Okay, now I still need to rely on your feedback and your response. So just try to give me some response so I know you are here. This is kind of important for me to, otherwise I feel like I'm really talking to nobody. That's not very fun. Okay, so this is a very important chapter. I think it's a very good time that we have this break, 1 week break, and today what we are going to talk about might be a bit abstract to some of you, and I will try to take you through all this quite carefully. Okay, so I hope you will really like it. I really find this result very beautiful. Okay, so again, just a quick recap this time. It was a while ago since we talked about thermodynamics. So last time, what did we cover? So basically, the entire week before the break, before the New Year break, it was all about Carnot. Okay, we talked about Carnot cycle, Carnot engine. Those I don't want to repeat. But towards the end of last lecture, we talk about Carnot theorem, right? As I say, everything to do with Carnot is very important in thermodynamics, so you need to know. And this Carnot theorem is particularly powerful. Just to remind you, what is this? This Carnot theorem is about the efficiency of engines, right? So this is this theorem is about the efficiency. Okay, so I gave you the statement. You can read it yourself, but I'm going to read it for you without writing it down. This theorem tells you no engine operating between two given reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. Okay, so this statement, we spend time to understand. We spend time to really dig deeper into that. Okay, so basically, what from this theorem we get this result. If you have a hypothetical engine which we label H, we can at most say something like this. We can say the efficiency of that engine can at most be the efficiency of the Carnot engine operating between the same reservoirs, the two same reservoirs. Okay, so all these are very important keywords. Okay, so if I have a hypothetical engine, I can only say that. And if I know a little bit more about this hypothetical engine, let's say I know if additionally, this engine H is also reversible, then we can have another inequality, which is the eta of H is greater or equal to the eta of Carnot. So these two statements leads you to this conclusion. Okay, so this is the whole logic. Okay, so you cannot you have to be very careful when you try to understand the full statement. Okay, so we went through this, and then what else do we do? We use this Carnot theorem. We immediately use it to get something powerful. Okay, so this is from the Carnot theorem. So from the Carnot theorem, we establish a temperature scale. Okay, so this is called the thermodynamic temperature. Okay, so this is one thing we get. So after we got this, I also mentioned in passing that you can show that this temperature scale, thermodynamic temperature scale, is equivalent to the Kelvin temperature scale, which is based on the ideal gas. So when you write your PV is NKT, N times K, Boltzmann constant times T, that T is the same as this T here. Okay, so we just use one symbol T, which is the same as the Kelvin scale. And we can drop all these labels. I use the theta 1, theta 2. We just relabel to T1, T2. Okay, so this is one. And then the other one, we also able to extract these important ratios. Okay, so that is the ratios of heat transfer. Okay, heat energies for a reversible engine. So for a reversible engine, so this is what Feynman called the heart of thermodynamics. So let's write it down. So that is to do with the heat ratio. The ratio of these two heat energies, where QH is the heat exchange. You can think of it this way: it's the heat exchange between the engine and the reservoir at TH, and QL is the corresponding one at TL. So you can extract this ratio. Okay. So this is basically what I covered before the New Year break, and I also at the end of the lecture I spent longer time when half of you already left. I talk about the heat engine running backward. Those you can I hope you have time to watch the video and try to appreciate that part. Okay, that's not too difficult. Okay, but what we will try to achieve today. So today, our main goal. Let me give you a preview. We are going to get this important inequality. So this is called the Clausius. Today we are going to develop this. So this is called Clausius inequality. Inequality. Okay. Remember our goal. Our goal is to show this. So we are going to show that there's this integral, okay, around a closed loop. And this is d bar q is the infinitesimal heat exchange, and this heat exchange occur at the temperature T, and this is less than or equal to 0. Okay, so this is a very general statement, and this is called Clausius inequality. And at this point, now some people find thermodynamics difficult. The reason I think based on my experience of teaching this course for the past few years, I think the reason is this: people are not very comfortable with this kind of statement, inequality. Now you are very used to equality. You know, if you plug in all the numbers, you satisfy. Well, if the left hand side and the right hand side are equal, you're happy. You can get a concrete prediction. But here, this is also some kind of concrete prediction. You put in some number. This number has a range. It's not like an equality. You get T temperature has to be 500 Kelvin, that kind of certainty. Here, as long as this is very small, whether it's -5 or -5 million, this is satisfied. Okay, so this is a point to keep in mind. Now, when it comes to thermodynamics, particularly when we introduce a second law, a lot of this inequality begin to show up, and you have to learn how to appreciate this. Okay, so closest inequality is the big one which we want to cover today. Okay, I want to motivate you a little bit by looking at a slightly more familiar example. Just spend 5 seconds, try to maybe capture this in your mind. This is going to show up again and again, and remember our goal. Okay, so this is closest inequality comes from closest theorem. Okay, so closest theorem. Okay, let me motivate you. As I say, I want to motivate you for you to get this result. Okay. Okay, I'm going to take the recap this slide again. I'm going to borrow some result from last week. So this is precisely what I want. Okay, about the hypothetical engine again, a general hypothetical engine. Okay, so let me consider a heat engine, a hypothetical one. I don't know much about this. I only know that this engine operates between two reservoirs. Okay, so this is operating between T1 and T2. Okay, these are the temperature of the reservoir. Okay, the engine operates between two reservoirs, and the two reservoirs are at T1 and T2 respectively. So I'm going to call this the low temperature, and this is the high temperature. Okay, T1 is higher than T2, hotter than T2. So this is an engine you have seen 1 million times. Is this one here? Okay, this is what I'm going to use to motivate a simpler version of closest theorem. Okay, so this I'm going to we already established the temperature scale, so I'm going to call this T1 and T2, and you can use a usual interpretation. Okay, this is an engine. I don't know much about this. This is a black box to me. Yeah. Okay, but I know from Carnot theorem, I can write this down. Okay, so this is what I showed. I demonstrated last week. Sorry, 2 weeks ago. Okay, and what else can you do? Okay, on the left-hand side, we argue when we try to establish the thermodynamic temperature scale. I argue to you that this has to be related to the ratio Q2 divided by Q1. Okay, that is what I show. Right. So the efficiency for a typical engine is written like this. Okay, remember this? We define this is one step after the definition. We define it in terms of work done and Q1, right? What you get versus what you pay. Okay, and you get this result, and you can only write this down. You have to stop here. There's nothing much you can do. Okay, and then let me copy down a few more lines for you. So for the Carnot engine, of course, we can have the same result. Okay, but for the Carnot, I don't want to label C here. I want to emphasize that Carnot is reversible. This is the fact that we use many times. Okay, so this means this is reversible. So I should color code it for you. This is here, and this one is here. Okay. Okay. And when we work out the way to define the temperature using Carnot theorem, we establish that this is related to the temperature ratio at the heart of thermodynamics. Okay, so from here to here, this relies on the fact that we have a reversible engine, which is a Carnot. Okay, remember we use a Carnot engines to find the temperature. That is why everything I say is relevant here. You see, I give you a recap. This ratio is related to this reversibility. Okay. So for the reversible part, I can additionally write this down. So now I can collect the term. I can look at the whole line and then I can collect the term. I can write 1 minus Q2 divided by Q1 is 1 minus T2. Is less than or equal to 1 minus T2 divided by T1. Okay, so let me, to help you revise, I want to, maybe I will underline a few things for you. So this is really related to the right-hand side of the first inequality, okay? So far, so good? Okay, so just tidy things up a bit. I will have Q2 divided by Q1 is greater or equal to T2 divided by T1. Okay. Now, if you read Blundell, he got a little bit, you have to be careful. As usual, I always mention that you have to be careful about the sign convention. So he make a little bit of jump. If you are not careful, you might be lost. Okay, so remember here we are talking about magnitude. It better be, right? Otherwise, if we define this, if the sign convention has been properly accounted for, this cannot be a positive number, right? Because here this has to be positive. Okay, so therefore it's understood that we really meant the magnitude here, right? So in the past I put the absolute value to remind you. So here again, let me write it for you. So this is the magnitude. It's a very standard way to write things, and if you are not careful, you will make a mistake here. So I decide to take one more step to make it very clear. So now I'm going to take care of the time convention from now. Okay, I get this result. The convention, sign convention is taken care of by the arrow. Okay, now if I want to really make everything mathematically robust, I don't want to look at this diagram. I already get this result. So take into account our sign convention. This is really this convention we define when we introduce first law, sign convention. To be very clear, I need to introduce more symbol. So I'm going to call QH. H means high. Okay, I'm going to take Q1 to be the same as QH. Okay, heat enter the system. Heat enter the system. Okay, and QL, which means low, this is low. And I'm going to give it the minus sign. Okay, heat leaves the system. You have seen this before. I have done something similar before. Okay, so now putting in all this sign convention, I will have Q2 is minus QL. And then Q1 is QH. It's bloody annoying. I have to introduce more symbol, but it's better this way. And this has to be T2 divided by T1. Okay. Okay, T2 is low, T1 is high. So now I can get the inequality I want. So I will have so I can move. So first I form the ratio I want. So I will have QL over T2, QL over T2, and QH over T1, and I move everything to the right hand side. I will get this result. Okay, so you can easily check that this is correct. Okay, now look at this closest theorem, closest inequality. Okay, now I basically give it to you, right? So what I have is a simpler version. So what I have now is I will have the sum over Q at each segment, right? That's why this 1, 2 has the meaning. So I am going to use this I to denote, to label the reservoir. Okay, so I will have something like this. And this has to be less than or equal to 0, where this I really run over the entire cycle. Okay, so here I only have I equals 1 and 2. You can imagine this engine is exchanging heat with 2 reservoirs, right? This the way to appreciate this is, remember your PV diagram. PV diagram. Suppose this engine is based on the gas, right? I can draw isotherm adiabat. Right, so this is really running through the cycle, right? So I exchange heat with reservoir at T1, so we know this is Q1, this is Q2. We already showed this, right? So you run from here to here to here to here to here to here. So this is really a cycle. So you first exchange heat with Q1, then you first exchange heat with T1, then you exchange heat with T2. Okay, so you run through the cycle, and this process is equivalent to that. Okay, so if you now use the differential to express the infinitesimal amount of heat that you can extract from T1, then we get this result. Okay, and then this is the closest inequality that you have already known. You just don't see it this way, right? Because you know this Carnot theorem, you know the Carnot cycle, you know the heat engine very well. This is all you have, right? So you already know how to deal with this. Okay. Now I want to make it very general and therefore more powerful. So here we need a new slide. Now for a real engine, let's call this a more realistic engine, not necessarily the engine you build. Right? For engine, more complicated engine, you can imagine that you can exchange heat with more than 2 reservoirs. Right? You can have a huge cycle that you can keep exchanging heat. Right? So that would be a more general engine. So let's call it a more general engine. So a more general heat engine. And we also want to run it in cycles. So we are looking at cyclic process. So let's now consider a general engine operating in the cyclic mode. Okay, we still want to show this result I previewed to you. Okay, so now how do we do this? I'm going to draw this engine. I have a more beautiful picture in my note. So I'm going to draw something like this for you. Okay, so let's assume we are going through some cycle. Again, you can think of this kind of PV diagram before, right? So now I would generalize it, and I'm going to assume that at some segments of the cycle. So let's say I have this segment here. Okay, at this segment, the engine is exchanging heat with a reservoir Ti. Okay, and so there's to say I make it more abstract now. You see, so now I consider a process which allows me to extract heat d bar q I from the reservoir Ti. Okay, I say extract. Basically, you should imagine this as exchange. Okay, so this is a more abstract way to draw it, and then I need to give some output. So this output will be work done. Okay, so this diagram, if I take I equals 1 and 2 only, that will be my Carnot. That will be my usual heat engine. And if this process is everywhere reversible, this will be my Carnot. Is it okay? Right, this is how I want to proceed with this. Okay, so for this general heat engine, what I will then have is I will have d bar q 1. This is the heat exchange with a particular segment of the cycle, particular segment of the cycle. Okay, so this I really is for me to do accounting. This is an index I introduce. So I will label I from 1 to 100 or whatever. As long as I can identify each segment, that will be okay. Okay, and then you should also at this point, now the more power, this is very powerful. Okay, so now you should keep in mind that this segment I can also be non-reversible, irreversible. I do not say it has to be reversible. Okay, so this segment, but of course you know what I'm going to say later. Of course, later I want to generalize it to the reversible statement, but at this point you need to keep in mind that this is the logic here. So the segment can be irreversible. Okay. Okay, there's a question. I don't know whether you can see. The question is, we only count the heat absorbed in this diagram. How about the heat goes to the coal reservoir? Okay, the heat goes to the coal reservoir can be accounted for, right? Let's say I have we take the heat engine we described earlier, right? The typical one, the exchange that this engine. I will have I equals 1 and 2. Okay, and then I can easily flip the direction of the arrow. Then there will be heat leaving. And I do not say anything about I do not say anything about the relative size of Ti. Okay, I can set T1 to be 100 Kelvin and T2 to be 50 Kelvin. Then I will have the heat engine, the setup of the heat engine I discussed up to now, up to the previous slide. Okay, now if I have answered your question, please give me an indication. Now the student who asked this question, this I is not just 1. Yes, DQ can change sign. Right now, we do not say anything yet. D bar Q, sorry. All right. Okay, thank you. All right. So I try to repeat the question for the rest of the class. So the question is, okay, let me rephrase the question. So can I use this diagram to describe this? The answer is yes, I can. Okay, I would take I equals 1 and 2. I will set my TI to be I set my T1, T2 to be some values which I can decide later. I can set my T1 to be larger than T2, and then I can also have D bar Q1 to be of different sign compared with D bar Q2. So this is a very general set, very abstract if you like. But in this case, it's more powerful. Okay. All right. So what is the work done? Remember, I want to operate it. I will write this. What is this work done? Okay. The work done in this diagram is simply the sum of D bar Q I. Okay. But it's not just summing any random I. I have to sum over all cycle. Okay, I hope you can immediately see that this has to be true. If I have if I operate like this, go from some states which I label A, I go to B to C and then back to A, I must have this result. Why? Because du has to be 0. Why do we have du equals 0? Because du has to be 0 for a cycle. Why is it the case? Because U is a function of state. And what do we call this law? This is simply first law. Okay. All right. So now I want to introduce something else. Now you have seen many times. Again, sorry, I keep drawing this kind of diagram. I want to have a way to do accounting. I want to count this D bar Q1, D bar QI. Okay, so I know if I want to do something like this, I need an engine which I know very well. So I'm going to introduce a Carnot engine. Okay, so I'm going to introduce a Carnot engine. You can also think of it this way. I want to use a Carnot engine to supply D bar QI for the reservoir TI. Okay, so this Carnot engine is very specific, right? This Carnot engine has to output this to TI, so I need a different Carnot engine for different I, so I need to introduce the index I. Okay, so I'm going to bring in a bunch of Carnot engines. They can all be the same brand for buying from the same company. But I'm going to use them to keep track of the heat flow for the ith reservoir. Okay. And one thing I want to do is I'm going to connect all these Carnot engine, all I of them, to the same reservoir, T fix. Okay. So be careful. TI, T sub I can change, but T fix cannot change. This is a big reservoir I demand. This can, for example, be the river, Shatin River. I plug all the Carnot engine with one port to the river, right? It's a huge reservoir. Everybody share the same temperature. And then I'm going to connect the other port to the reservoirs that can change temperature. Okay, so let's complete the drawing. If I do it like this, I will also get some work. Okay, so this has better carry the index I because there's an I here. Okay, so the red part is Carnot. So up to here, this is a Carnot. Okay. So for let's look at C sub I. I'm going to use the heart of thermodynamics, the one I mentioned before, which allows me to write down the equation for the heat ratios. Okay, but I don't want to introduce another symbol here, so I'm going to just write the heat ratio like this. So I will have d bar qi plus d bar w, right? So this split into two. So this is the sum of the two. Okay, so I have this heat exchange at T fixed. And this has to be the same as d bar qi at T sub I. Okay, and this is what? This is this one. For a reversible engine. I just plug in a reversible engine, which is Carnot. Okay, so now you need to trust me. I will just copy this down. You can check by yourself. So this is T fix. Ti minus 1 d bar q. Okay, so this is just rearranging this. Okay. All right, now I'm basically done. So again, this is a standard trick for this kind of material, right? I want to look at this engine. I'm going to look at this as a composite engine. Okay, so I'm going to look at this as a composite engine. So what is the best way to do it? I will maybe move it here. And then this one is, let me use a different color. You can look at this like this, right? You can look at this as everything is internal. Okay, so I can choose to view this very complicated setup as an engine like this. I will have some heat exchange with T fix, and everything is internal. So I will just draw an effective engine. So I will draw a different shape, maybe a diamond. Okay, so this is a composite engine. So everything, all this I, etc., is inside, which I don't care anymore. They are composite. It's like a black box. I don't really want to open up my engine to see how many reservoirs this green cycle is exchanging heat with. I just want to look at the net result. Okay, so in this case, I will have a net result which output the work. Okay, but I know the work comes from this because the Carnot has some work, so I will need to pick up. And then I also want to collect this. Okay. And more importantly, I want to stress that I want to look at work per cycle. So work per cycle means I will have to sum over the cycle, right? So this is the first element, the second element, the ith element, the 100 element, and then we come back to the cycle, right? So the sum over this will give me the work per cycle. So this takes the meaning of work per cycle. Okay, so this takes the meaning of work per cycle. This is total work done per cycle. All right. Okay, now I hope you sense that there's something profound here. What is this monster? This monster is exactly what we do not want. This is the engine which violates the Kelvin statement because we take all the heat and convert everything to work, right? Now, this is T fix, a single reservoir, which we know is not allowed. A proper heat engine will need at least 2 reservoirs. And then where's the second one? It's not there anymore because everything is internal to this composite engine. So this is a violator. This engine violates the Kelvin statement. Okay, so how do we rescue the situation? So let's rescue the situation. So let me write this down. Okay, the total work done is this. So I will need the total work done. So the total work done is delta W plus sum over cycle. Okay, so this is all the I in the cycle. Okay, so essentially this is summing over the cycle. Now, if I set this to be like this, which is like what I drawn here, then this is indeed a violator. Okay, but if this is like this, it's okay, right? So let me say this again. Again, as you need to understand the sign convention is absorbed in the arrow. So this means I take everything from T fix, and then I demand the output like that. Okay, this is the magnitude of this output, this work done. Okay, so if I can get really extract work from this system, then I violate the Kelvin's statement. And therefore, to rescue the situation, I have to demand this bit to be negative or 0. And this, you know, is okay. This is like a hairdryer, right? If I flip the arrow, this two and this, I flip these 2 arrows. This is a hairdryer. I take my machine, plug it into the wall, and then I can dump some heat to the reservoir, and this reservoir can be me. This is allowed. Okay, so this is so to fix the situation. So to fix the situation means we do not want to violate the second law written in the form of this statement. So to fix the situation, we have no choice but to demand this. Okay, and now we are done. So let's the key of the argument is done. The rest is just writing down the mathematics. Okay, what is delta W? Delta W is here. Okay, let's go and collect all the terms. So this is sum over the cycle d bar q. This is we already showed that this is we use the first law to do this. Okay, and what is this? Sum over d bar wi. And d bar wi is this. We want to sum over all i's such that we form a cycle. So we need to copy this down. Okay, so we have t fixed over ti. So we have to sum over cycle again. We have t fixed over ti minus 1 d bar q. Okay, so again, let me help you a bit for your revision. This is this, and this one is this. Okay, and this whole line has to be like that. Okay, we don't need an engine anymore. Now we can focus on this, and now you can you just manipulate the line. So you have sum over I, sum over I d bar q I, sum over I d bar q I with a minus sign. So this is gone. Okay, sorry, I don't want to draw it like this. Yeah, this minus 1 is gone. Minus 1 times this. Okay, so all you have is sum over I in the cycle. T fix, Ti, D bar Qi, this is less than 0. And I already told you this T fix is fixed. It's a constant, so you can pull it out. And this is a positive number, so it doesn't change the inequality. So you get the next line, sum over D bar Qi. Okay. Now we sum over this I in the cycle, and then we have this kind of differential. So it's conventionally written like this. So that is to say, we do this, basically we are doing this accounting for the closed path in the indicator diagram, and we will get this result. So this is what I want to give you. I want to present to you. This is closest inequality, important inequality. So let's box it. No. Okay, so this is closest. Okay, and sorry. Once we switch to integral, we don't need this index anymore, because it's understood that we are doing we have this segment which is infinitesimally short. Okay, so this is a very cool result. And what else can we say? Now, what else we can say is the following. This is what I promise you. Remember, at this moment, up to this point, I did not say anything about reversibility. And now I want to make this statement stronger. But this is a very strong statement, and you need to pay attention. So if the system, which means this cycle you are looking at, this one here at the top, this one, if this cycle is reversible everywhere, so it's reversible everywhere. If you have one very short segment which is not reversible, let's say I equals 5, very short, but annoyingly is not reversible, then the only thing you can say is this closest inequality. You have to stop here. You cannot say anything else. But that's why this is a very strong statement. So if this is the case, then for all I, not just one of 5 I's, or for all I's, I can flip the direction of the arrows in this diagram, right? Whether arrow is pointing away from the system to the reservoir or pointing from the reservoir to the system, I can flip all of them. I'm allowed to do this. Okay, so in this case, this is essentially saying that I can change the sign of D bar Q. I can change the sign of D bar Q for all I's. And if you change the sign, you introduce a minus sign, this inequality flip. Okay, so this again is an additional requirement because of the notion of reversibility. So we additionally, let me highlight this word again, additionally have this result. D bar Q has to be greater than 0. Okay. All right. So you can only satisfy these two requirements if you have an equality. Okay. So this tells you you have to set this to 0. Okay. So to remind you, I'm going to do the same as before. I'm going to write REV for reversibility. So this is only true if I demand reversibility. And for the for any general process, I will have closest inequality. For a process, if the process is completely reversible, I will have this equality. Okay, so this is another one which you have to take home and then appreciate this. Okay, and I'm going to say one more thing and then we take a break. Now look at this. Now look at this last equation. Now this is really an equation. It's really equality. What does it remind you? I hope if you follow this, at least at this moment, I hope at least your blood will be boiling, because this is it's very exciting. This link everything from lecture 1. What does it tell you here? This line. What do we mean by a kind of state? Right, exactly. So it means this integrand here is path independent. Okay, I can choose any path. I make it very general, but here you have to appreciate this. I can choose any path, and I will be able to calculate this ratio, not just d bar q, but d bar q divided by t. And I will be able to calculate this integral by only choosing the endpoints. That is to say, I'm allowed to define a new differential for this. And this differential is an exact differential without the bar. It's an exact differential. And I'm going to call it the entropy. Okay, so I'm going to define, now right now it's a symbol, just a symbol, right? But it carries a lot of meaning. I'm going to define this. Okay, so that is to say, by studying this engine, I discover the notion of entropy. This is the first time we really have this quantity properly drops out from this analysis. So we discovered something called the entropy. Another way to say that, if you like, is we found the integrating factor for the inexact differential d bar q, which is something we hate at the beginning. And it's our goal to find the integrating factor, to turn it into an exact differential so it's easier to do calculation. Okay, so this is S is a step function, which we call the entropy. So S is entropy. So this is a big moment, I think, for this course. All right, so now is a good time to take a break. So let's take a 10 minutes break. We come back at 12:40, and then we are going to learn more about this entropy business. Okay, so see you 10 minutes later. Okay, welcome back. So now I received a few questions on the chat. They are rather long, so I will be brief. Okay, I will summarize the key points for the rest of the class. So it's about this T fix. So this T fix is really you know who you are. You use a very nice word here. This Carnot cycle, does it really affect the cycle we want to discuss, right? After all, let me bring the picture out. So what we really want is to discuss the cycle in green color. Why do we introduce the Carnot in red color? So this is like I use the word accounting, but this is maybe a better word is bookkeeping, right? This is really a machine we know very well, and it's a very cunning way to try to construct an engine which will lead us to some violation. And then we try to use the method we learn all along to try to fix it such that we don't violate the second law. Okay, so this violator, the Kelvin violator, is something we do not want, and therefore it's a way, if you like, it's a way that allows us to construct this. And the fact that this kernel is really not in the end not affecting the green cycle is the fact that, you see, I introduced now what is specific to these CIs. Okay, these CIs are connected to this T-fix, right? But in the end, this T-fix is gone anyway. If you look at the mathematics, so from here to here, so at this part, kernel is still playing a role, right? Because this T-fix is associated with one of the reservoirs of the kernel engines. Right? There are many kernel engines, right? They all share the same T-fix, and this T-fix is gone anyway. So we just want the inequality. Okay. So this the student who summarized it in a very long chat, you are correct about this point. Okay, and your understanding is also perfect about this T-fix. So this student Chen, I cannot tell whether it's Mr. or Miss Chen. Okay. And then the other thing is, as I say, this is you can think of this introduction of this kernel as an auxiliary argument. I just want to come up with this composite machine shown in the middle, right? Nobody can stop me from connecting kernel. I have lots of money. I can buy tons of kernel engines. I can connect it the way I like. I do not violate any laws of physics, so I can do it this way. But it turns out that after I do all the proper thing, I ended up violate the second law. So I need to fix the problem, and that is why on the second diagram shown in blue, the only thing I can say is I will have to demand this arrow to be pointing towards the engine. Okay, and where does the energy goes? In this case, if you look at this, the only way you can go is you also need to flip the other arrow upward, going to the T-fix, right? Because composite engine is very complicated inside. We don't know what is happening. But if you look at this simple diagram, the only way not to upset the second law is to really have the energy. The only way not to upset the first law is to respect the energy conservation. Okay, the first law is always there, right? If you look at the middle diagram, as I already said, if you look at the middle diagram, it does not violate the first law. It's okay, right? I have some energy coming from T-fix to COM, and then from COM to elsewhere, fine, right? But it doesn't happen it doesn't happen in real life. This is because you have additional thing called the second law. Okay, so I hope this additional comment will be useful for some students who send me the messages. Okay, so now coming back, let me refer to my slide in chapter 4. Now anyway, I don't remember which one, but this is a summary. Okay, I hope this is okay. Please let me know if it's not. Okay, so this is a statement, right? This is the full statement, and this equality is only true for the reversible cycle. Okay, so for the most general case, this is the best you can say. As I mentioned, you need to include the inequality, and you need to include the equality in the most general case, so you can account for all different scenarios. Okay, so now what do we gain from this exercise? So first, let's look at the new quantity we discover, right? We really discover something, and this new quantity is what we call the DS, the change of entropy. And this has to do with our definition. We define it with respect to a reversible process. And this temperature T, I want to emphasize a bit, so I will make a note here. So this T is really the temperature where the heat exchange occurs. So this is temperature where heat exchange occur. This is not the system temperature. Okay, so usually we use a reservoir to model this, right? Because we know we can artificially boost up the heat capacity of this object, which we call the reservoir, and to have a stable temperature. Okay, so I hope today we can get to the point to see how to use this. So there are a few more items to discuss. So what is S? S is entropy, and S has the unit. The unit of S has the unit of you have heat, and you have heat energy at the top, and then you have temperature at the bottom. Okay, can it be measured? Now this is a very important question. Can you measure this quantity? Now whether we can measure or not, we need to first see whether this S makes sense, right? Because now, up to now, we talk about the change of S, which is the change of entropy change. But can we say that at a particular state we have entropy value S of several joule per Kelvin? Okay, so this requires some analysis. So first, if you have a process from A to B, so let's say you have a process that takes you from A to B, process from A to B. You can do a bit more with this. What can you do? You do something very simple. You can integrate. Right now, you're powerful. I gave you a step function. I gave you a step function. You don't need to ask me about the path. You know how to do it. Right? So you don't care about the path, and this is simply a change. So at this point, we only know how to define the difference. Right? We do not have a mean to isolate one of the entropies out. So we only know how to define the difference. So if you want to get the absolute value, so to get absolute value, you need some fixed point. So to get absolute value of S entropy, you need some fixed point. So you need to get a fixed point. And this fixed point is related to the third law of thermodynamics. Okay, what does it say? According to third law, you can get this result. The absolute entropy has to go to zero at zero temperature limit. So this gives you a way to manipulate your system. It depends on the system you want to study. That gives you a way to choose a fixed point, and then you get a scale. Okay. And if you look at this system here, now if I have a system where the reversible heat exchange is zero, then your DS will automatically be zero. So this process, if you have a process that gives you this process has a name, just like we have isothermal, adiabatic, isochoric, and in all this in thermodynamics, you have other terms for, you have another term for this condition, and this is called isentropic. Okay, so we have basically all these, which we which allows us to begin to look at entropy change. Okay. So right now, I still want to talk about entropy change. I don't want to talk about the absolute value of entropy yet. Okay, so entropy change, please keep this in mind. Okay, at this point, I want you to appreciate something. We finally have a tool to tell whether a given process is reversible or not. That is to say, sometimes we talk about whether a process is possible, right? Let's say if I can have heat transfer for one direction, we will ask whether the other direction is possible. So how do we handle this situation with our new tool? We just analyze whether such a process is reversible. Okay, so if you have heat transfer from A to B, you ask yourself whether this heat transfer, this process is reversible. That is equivalent to saying that the question is rephrased to whether heat transfer from B to A is possible. Okay, so this is the process which does not violate the first law, but second law gives you additional requirement. Okay, so that is the business of irreversible process. Okay, first, can we even define ds for such a process? Okay, so let's say I will give you a general diagram. Okay, I'm going to take you from A to B, a process from A to B. Now you can think of it as a PV diagram again. Okay, I can go from A to B, right? But think of it in a more general term. I suppose I will be able to indicate the change from A to B, like this. Okay. And suppose there's some process which I know is not reversible, but it also takes me from A to B. Okay. Because it's not reversible, I don't really know how to draw it on the indicator diagram. Right? Can you think of an example right now? You can type to me something you have learned before, which we can draw on the indicator diagram using both the solid line and the dashed line. So dashed line is not reversible. So this is not reversible. And this is reversible. That example will help you to understand this. So if you know the answer, type to me. Okay, so I'm going to proceed when you are sending me your answer. Okay, so now let's apply closest theorem. Closest theorem tells us this is true. Okay, so what do I mean? Okay, how do I apply it on here? Okay, so I want to my M here. What is my M? My M is to borrow the result of the reversible process to try to understand what will happen to the entropy change for the irreversible process. And both processes have the same endpoints, A and B. Okay, so what I will do is I can do something like this. I can first go along the top path. Then I come back to A, right? So I want to go from A. Now I will draw it very nicely for you. I will go from A through the non-reversible, irreversible path to B, and then I want to go back to A with the reversible path. So this is the this dashed line is really not reversible. I want to do it like this. Okay, so this is my cycle. Okay, let's do it. So for the first segment, I just write it down. I go from A to B. D bar Q T. I cannot do much more. This is all I know. Okay, this is the best I can do. Okay, so this is a dash line. Okay, but when I get to B, okay, I will write this from B to A. I will have D bar Q and T. Okay, to remind you, I'm going to draw this solid line, and then I'm going to label this. This is a reversible process. Okay, so this is a complete loop, and I must apply closest theorem. Okay. And next, what I will do is I don't know how to deal with the first line. I just don't do anything. Just keep it. And for the second one, for the second line, I will flip the limit. So I will go from A to B. I flip the limit. I need to introduce a minus sign. So I will have this. Okay, so this allows me to write this. Okay. All right, but I did not tell you how far is A separated from B. So A and B can be very close, can be very far. So this result should not depend on the integral, right? So however close they are, I will have this last line. So for this last line to be true, for any A, any B, I have to demand the integrand to be to satisfy the inequality. Okay, I flip already. So this d bar q ref divided by t has to be greater than d bar q divided by t. Okay, so now be very careful. If it's the first time you see this, you might not keep all this in mind. And which one is the definition of ds? And this is the one point that you can get seriously wrong if you do it the incorrect way. So we define ds based on the reversible process, right? The step function business. Okay, so with this is the same as this, and ds has to be larger or equal to dq over t for a general process. You can easily convince yourself if this dashed line becomes reversible, you will have the equality. It will be a trivial result. Okay, so this is a key. So this one describe a process which might not be reversible. So it's a general process. Okay, so because it might not be reversible, it's necessary to assume that this is not reversible to begin with, to be able to discuss the most general case. Okay. All right. So this gives me some tool to tell whether a process is whether the reversibility is allowed or not. Okay, so this leads to a few statements. A few statements that is also related, sometimes used as the statement for the second law. So let's have a look. Okay, what are the statements? I should have written this a little bit downward. Okay, if you have a thermally isolated system, so if you have a thermally isolated system, what can you have? You cannot exchange heat for such a system. I have a system. This is thermally isolated to the rest of the universe. Then I cannot exchange heat, and there is no way for this d bar q to be active, right? So I will have d bar q to be zero, identically zero. And this leads to a very standard statement of the second law. You have this, the change of entropy is greater or equal to 0. Okay, right? So in a simpler term, under this condition, we say that the entropy of the system can only increase. It cannot decrease. Sorry, let me make it more precise because of the inequality here. Okay, for such a system, the entropy cannot decrease. Okay. Now, before I move too far, I want to collect the answer I asked earlier. I asked you, how do you have two processors like this that allows us to link this kind of abstract argument to? Okay, I see some nice answer, and this is the Joule expansion. And the free expansion, I can imagine. Let's just take the ideal guess. Expand from A to B. Sure, I have the initial volume, I have the final volume. I know how to go there. Okay, and that is not reversible. But I can also imagine or dream up other processes that takes me from there. And for example, isothermal expansion can also take me to the same state. Okay, so this is indeed the trick we will use when we analyze the Joule expansion. So that is a classic example when it comes to irreversible process, right? We are going to apply the tool to test that whether Joule expansion is reversible. You do not see Joule compression. You do not see all the gas suddenly compress simultaneously to one smaller volume. Okay, this analysis later will show you why. Okay, so just stay with me and we will get to that point. So let's finish up a few definition. Okay, so this leads to the second law, some statement of the second law. Let me see if I have convenient writing for you. Okay, I will write it. I cannot find it now. So there are some equivalent way to say this result, and they are all called the second law. So second law of thermodynamics. Apart from those engines, you can also formulate it based on the entropy argument. Okay, and I hope you appreciate that they are all equivalent. Okay, so this is the case. So for a thermally isolated system, the entropy either stay constant, so either stays constant, right? Constant means ds is 0. Look, there's this allows the possibility. Okay, so either stay constant or increases. Okay, so this is basically this line here, but let's sharpen it. When do you have a constant entropy, ds equals 0? ds equals 0, you come back to here. When do you have ds equals 0? That happens when the heat exchange is reversible, but then you isolate this path. Okay, so this would be either stay constant for reversible change, or increases for an irreversible change. Okay, and the other statement is again the second law. The entropy of an isolated system and this one, please think a little bit. Okay, it tends to a maximum. All this comes from this line here. Okay, I'm trying to attach meaning for you. Okay, so please think a little bit. Now, this one is kind of obvious because it's really just translate the mathematics into a language, in English language. This one, you think a little bit. It's not too difficult. Okay, in Blundell, there's one statement which a lot of students like because they find it very cool. Okay, so I'm going to give that statement. If the universe is a thermally isolated system, then the following are true. One, the internal energy of the universe is a constant. I do not have a way to inject energy, neither by work nor heat transfer, to increase the internal energy of the universe. Okay. Second, additionally, now this is about the first law. A is about the first law. And second, the entropy of the universe cannot decrease. Cannot decrease. Okay, and that is the same as ds is greater or equal to 0. Okay, now let's do some calculations. This is really let's look at a concrete example. Now all this needs to be put on a proper context for you to appreciate how cool this second law is. Okay, so I'm going to talk about the universe like this. So this is an example. It's a very important example, and you must learn how to do it. Okay, so I'm going to take my universe to be a very simple combination. So I'm going to look at the system plus the reservoir. So a system which I don't know the detail, and a reservoir which I also do not know the detail. It's just a reservoir. Okay, so you can think of it like this. This is you might want some want to help you to imagine this. Just imagine this to be a small system and a large reservoir. That's the easiest way to visualize this. Okay, so let me so the reservoir, initially the reservoir is at temperature T reservoir. Okay, and the system initially, so this is initial, is at temperature Ts. S is system. Okay, I have a reservoir, I have a system. They're initially respectively at this temperature. Okay, and now I'm going to place them together such that they are in contact, in thermal contact. Okay, and then in the end, when I wait long enough, both of them will end up at the temperature of the reservoir. Okay, so the easiest way is for you to imagine a large reservoir in a small system. Imagine, I don't even need this word, just the reservoir has a lot of capacity, a lot of heat capacity. Okay, and this is a process which goes like this. So this is the arrow of time, if you like. The time goes this way. Originally, they are prepared in this form and then in contact, and then they are in both end up at TR. Okay, and you are asked to calculate a few things. I want you to calculate the change of entropy for the reservoir, the change of entropy for the system, and the change of the entropy for the universe. Okay, so this is your task. I would like to start this calculation as usual, as last time. If you need to go, you can go, you will see the video, and please watch the video because this is so important. And it will be better if I at least do something here so that the flow is not interrupted too much. Okay, so I will calculate this now. So I need to put some symbol. So I'm going to look at the heat transfer from the reservoir to the system. Okay, so this heat transfer, I will call it delta Q. Okay, there's some heat transfer from the reservoir to the system. Now, right now, be careful. I do not say anything about the relative sign of this TR and TS. And that is the cool thing. After I calculate this, you will get the famous result. This is something you learn in school, that heat flow from hot to cold. And how do you know? And this example tells you the result you expected since maybe high school, since childhood. Okay, so now I do not say anything about the relative sign of TR and TS, but I'm going to, and this heat transfer, the direction of heat transfer will just automatically come out after I apply the second law. Okay, so I need to define this first. Okay, I assume this to be given by that. Right, so this is a reasonable way to write this, right? I need to know the heat capacity, and heat capacity, I assume it to be a constant. Okay, so I also assume a constant pressure, isobaric heat capacity. This is not too important. Okay, just assume there's a heat capacity that I can use to describe the thermophysics of this problem. So assume constant. And I can easily imagine a isobaric situation. I just open everything to atmosphere. Okay, so this is a heat capacity of the system. Heat cap. Okay, you can imagine this line to be true, right? So this is the definition of heat capacity. Right? How much heat you can transfer and the temperature difference. Okay, so let's calculate delta SR. So this is the entropy change for the reservoir. So let me just write this down. This is we already know how to write this. This is d bar Q and T reservoir. Okay, in principle, I should write dq divided by T. Indeed, I have to do that for the system, but for the reservoir, according to the definition of reservoir, you can do a lot of heat exchange and the temperature will not change. This is the definition of the heat reservoir. Okay, so this T becomes a constant. Okay, and that's the reason I put TR rather than 1 over T. So be careful here. And the second thing is because this is 1 over TR and this TR is fixed, I have the advantage of pulling this out and I can just do something like this. Okay. And this integration is simply delta Q. But then I need to respect the sign convention. This is with respect to the reservoir. So I need to, now this is the heat transfer I define from the reservoir to the system. So if I want the heat to enter my reservoir, according to my sign convention, I have to take the negative of this. Okay, so I have to take the negative of this. Okay. And now just I will just call this C rather than CP. It doesn't matter, as I say. So this is C divided by TR, and I need to flip the sign, so this becomes TS minus TR. And I'm going to manipulate this. This is a very standard example. Any respectable book on classical thermodynamics must have this example. Okay, so you get this result. Okay, but I like to write it this way because this ratio allows me to very easily see whether the system temperature is higher or lower than the reservoir temperature by looking at the ratio. So I'm going to call this X. So this is C X minus 1. Okay, this is a little bit more complicated because, as I already say, I need to really write T rather than TR. There's no I don't really know at the particular instant what is the temperature. Okay, so so according to this definition of D bar Q, this is D bar Q is related to C heat capacity times DT. Okay, and divided by T. And now I need to worry about this. So originally, you see, I look at here again. Originally, my system is at temperature TS, and it will end up at TR. So I need to do this integration honestly. I cannot have the shortcut. Okay, so this is done, and I have a simple 1 over T. So I will get the log. I will have C log TR TS. Okay, and if I use this definition for this ratio, this line will become minus C log X. Okay, and now what is the change of the entropy for the universe? The change of the entropy for the universe is simply the sum. Okay, so I use this X for a reason that will become clear later. Okay, so I will have C X minus 1 plus C log. Okay, now is your job to show by doing proper calculus to show that this line is always 0 or positive. It cannot be negative. So this is a key result. This is a key result. Let me say in word. I have a system, right? So this I have a universe. My universe is thermally isolated. This is what I define as my universe. There's nothing else except these two. Okay, so the entropy of the universe cannot decrease. So I must get this result. Okay, so the entropy of the universe cannot decrease. I must get this result. Okay, but if you look at the system and the reservoir, you can easily see that it will change sign depending on my X. This is the ratio, depending on whether TS is, depending whether I have cooling or warming. Right, so this delta S of R can change sign. So the statement is very, very precise. So please, if you are still with me, be very careful about this statement. Delta S of R can change sign. Delta S, the change of entropy for the system, can also change sign. This log can change sign. Again, it change sign where? It change sign when X is 1. So you have two functions. These two functions change sign exactly, precisely at X equals 1. Okay, so the entropy can change sign. Don't come and tell me that the change of entropy has to always be greater or equal to 0, unless you invoke the condition that I have a thermally isolated system, which by the way is our definition for the universe. Okay, so what is the key here? The key, there are more. There are there are more to this. So I'm going to, I encourage you to use some calculus to show that this cannot be negative. But the other thing you can do is to simply plot all these functions. So you plot delta x, s, and versus x, which is the ratio, this ratio here. So you will see for the reservoir, this is a simple straight line with a slope c. I don't know what is c, so I will just label x equals 1. It will change sign at x equals 1, like this. All right, so this is reservoir, so I will label R. And the system is a log. A log I know how to plot, so I have a minus sign in front, so it would turn a little bit upside down. It will turn like this. This is my minus log. It will also change sign precisely here. So this is system S. And beautifully, this, when you add them together, now this is a little bit positive. You have some negative contribution, so it has to come a little bit lower. So this is the universe. The universe is so smart that it would precisely choose not to cross the horizontal axis, and it will come up like this. So this is the universe. So this is the entropy change of the universe. Okay. There are a few messages to send here. So you can then discuss the sign, whether you have x greater than 1 or x equal greater than less than 1, whether you have cooling, you have warming, and you can discuss the direction of the heat transfer. There are many things that can be learned from this example. So right now, I just want you to get the correct message. This is a very important concept, that the entropy, this line, the entropy cannot decrease, is only applicable when you have an isolated, thermally isolated system, which is what the universe is for. Right? This is not a thermally isolated, otherwise you cannot exchange heat. And in that case, the change of entropy can indeed be negative, as shown here. Okay, but even with all this process, you put them together, and the universe is still smart enough to respect the second law. All right, thank you very much. There's a good time to stop.